So hello viewers, I am Pratik Bhatt from Bharat Serums and I welcome you all on behalf of Bharat Serums to the 26th episode of ART Masterclass Season 1. Today we have with us Dr. Priya Kannan, who will be talking to us about the strategies to improve survival and success in cryopreservation. Talking about Dr. Priya, her name is synonymous with academics in India. She has done her MBBS, MEd from University of Sydney and she has done her MCE from the very reputed Monash University, Australia. She has been the past president, Academy of Clinical Embryologists India. She is currently the IVF lab director, Garbha Rakshambigai Fertility Center, Chennai. She is on the executive committee member, ESAR. She is a reviewer, Journal of Human Reproductive Sciences, and has authored many chapters in textbooks and leading publication houses. So with this, I hand over the session to Dr. Priya, and I request the audience for any questions during the session, please use the chat box for your questions. Over to you, Dr. Priya.
Thank you so much. And without much ado, I would like to go into the topic. And before that, I would like to thank you for inviting me to give this very lovely talk. And it's a very pertinent and important one. So cryopreservation, has it been just around now? No, it's been around for a very, very long time, ever since time immemorial that we knew that animals go into hibernation and come out. We just didn't know how it happened. However, the first case of successful mouse embryo cryopreservation by slow controlled freezing was reported in 1972, and ultra rapid freezing, as we know of now, the vitrification, was developed in 1985. That is just one slide which shows all the developments that we've been having since a lot of time, especially from 1972 when we had the first slow freezing of the mouse embryos, and then we had in 1984 the first recorded first birth from the slow frozen embryo, and then in 1985 we had vitrification of the mouse embryos. 1986 first first birth from the slow frozen human oocyte, so on and so forth. So it's been happening ever since. But however, since 1984, we have been started having cryopreservation in our clinical program in IVF. That is the first recorded child to be born from slow freezing, which is the name of the child was Zoe Leyland. Now, from none other than Professor Alan Tronson and Carl Wood. Professor Alan Tronson was my boss in Monash IVF. And with that, we started having the advent of cryopreservation in IVF. However, and I just wanted to mention that I had the opportunity and the honor of interviewing him for Meet the Guru like 2 months ago. However, we should not forget our own Dr. SUBHAS MUKHERJEE, who is probably the architect of the world's first baby born from frozen embryo transfer, which probably happened in 1978, like 2-3 months after Louis Brown was born. And we have Kanupriya Agarwal, or Durga, the India's first and the world's second test baby born through frozen embryo transfer. And it has been documented, and the same has been published by Professor Anand Kumar in 1990. Then we have this is the embryo freezing, and then we have a whole new history again about oocyte freezing as well. While we started with the slow freezing, right now we are doing much more with the vitrification. Now, coming to the question, why do we have to store? Why is cryopreservation important in IVF? One, because we do stimulate the ovaries. That is what is called controlled ovarian hyperstimulation, which means we have supernumerary oocytes and the possibility of supernumerary embryos is there. And we happen to transfer not more than 1 or 2 embryos. And what to do with the surplus embryos? Just can't be thrown away. To store them, cryopreservation is a great tool, which helps us to avoid multiple pregnancies. And of course, when there are legal issues, to store the embryos or store the gametes is a great idea. And fertility preservation. Fertility preservation can happen either in oncological or non-oncological situations as well. Oncological, we do know that it's of great benefit to the patients who have to undergo oncological treatments. Non-oncological, when there is an impending premature ovarian failure, or there are autoimmune diseases or infections, or when somebody is undergoing any sort of treatment which can be detrimental, which has got teratogenic properties, then it might be a good idea to store the embryos prior or the gametes prior to starting such treatments. And there are also other factors such as the environmental factors, exposure to gonadotrophic agent, surgical menopause, and most important that now which is happening now is social freezing, that is women wishing to postpone motherhood. That is another slide which shows us in one slide all the important applications of cryopreservation of oocytes and embryos in the program of IVF. So what and all we can freeze? We can freeze embryos from from 2 p.m., that is the fertilization stage, or day 2 embryos, day 3 embryos, day 5, day 4 embryos, day 5 embryos, and even hatched blastocysts we can freeze. We can also freeze oocytes. We can definitely freeze spermatozoa. Now we are also advancing into freezing ovarian tissue. So what are the principles of cryopreservation? What we have to understand, the basic thing we have to understand is all cells are made up of water. And most of that, 70% of cells is made up of water. Of that, 90% is free and 10% is bound to other molecular components. When we freeze, what happens to this water? Obviously, when water is frozen, it becomes ice crystals, and which we are talking about is the free water. The free water, it forms ice crystals and it tears through the cell membrane, thereby denaturing the cell. However, the water which is bound to the components of the cell does not freeze and is called the hydrated water. And hence, when we are trying to cryopreserve any cell, removal of the free water is of absolute necessity to avoid ice crystal formation, and the dehydration is limited to the free water. The removal of the hydrated water could have adverse effect on the cell viability and the molecular function, causing freezing injuries. What is the other effect of freezing? That is taking the embryos or the any cell to the, let us talk about embryos and oocytes in particular here, taking them to lower temperatures. The meiotic spindle is one of the most important aspect of any oocyte or any embryo, because that is what the viability of the embryo is dependent on. The microtubule system, the chain of the tubulin polymer, which holds the chromosomes in place, it is the meiotic spindle, and it is temperature dependent. And this polymer, when there is a lowering of the temperature, it causes depolymerization of these cells. And at 22 degrees, the tubulin arm completely disappear. And hence, we have to be very careful when you're doing it, that we have to do it appropriately, such that we don't damage too much. And as this process is reversible, the good point is the whole process of depolymerization and repolymerization happens when the embryos, when goes to 22 and below, it completely disappears. But when you bring the embryos back to 37 degrees, the repolymerization of the meiotic spindle happens. But if the process of freezing and thawing is not done properly, we can damage this, and hence rendering the embryo or the oocyte redundant, that is denatured. So what are the factors which can cause the cell injuries during the freezing and thawing process? Cryopreservation involves chilling and even freezing or vitrification in order to put their life on hold, which is what we call suspended animation, as we have known it from the movies, for either freezing or vitrification to maintain vital functions of the cells. Cooling, warming, and solute concentration must be managed in a way to favor the survival and to minimize the injury. Living cells can be injured by reduction in temperature, by the ice crystals, by osmotic forces, and also by chemical toxicity. We'll be seeing where every one of these toxicity or the factors do come into play. I'm just going to show you pictorially what happens when we are freezing. This is the normal cell, and that is the hydrated water, and hence there is some amount of ice crystal formation inside the cells. But if you don't have cryoprotectants or anything and you don't dehydrate the cells, what happens is the intracellular free water that is available inside the cells freezes and hence forming ice crystal formation. This crystal break through the cellular membrane and damaging the cells, which is one of the most common reasons of cellular damage in freezing. Whereas at minus 95 degrees, when the ice crystals forms in the cells, it can even cause the cells to rupture, which is why we should not have more than a certain amount of ice crystals inside the cells. To avoid such ice crystal formation, which is a way how to do it is by dehydrating the cells. Then we can't just dehydrate the cells. That means we'll be killing the cells. We have to replace the water available in the cells with some other chemical or some substance which will keep the cells protected. Those chemicals are called the cryoprotectants. They are additives which are used to protect the biological materials, cells or tissues or any of that from freezing damage. There are two types. One is the permeating and the non-permeating. The permeating cryoprotectants are low molecular weight and they are quite toxic at higher concentrations. They achieve their protective effects by increasing the unfrozen fraction at a given temperature and by reducing the ionic concentration. The common cryoprotectants that are used for IVF for embryos is DMSO, that is dimethyl sulfoxide, propanediol, ethylene glycol, and glycerol. The protective efficiency of these compounds vary from cell types to cell types. For example, the embryos are best frozen using a propanediol, while the blastocysts by glycerol, and so on and so forth. But nowadays, in all our free vitrification media, we do have a proportion of most of the cryoprotectants at some ratio. As I told you, there are two types of cryoprotectants. One is the penetrating, which are these low molecular weight cryoprotectants, which goes inside the cell and thus replacing the water in the cell with the cryoprotectant. The other one is the non-penetrating cryoprotectant, which is heavy molecules that cannot cross over the membrane, but then produce or promote cellular dehydration. The most common one that we use are the sugars, sucrose or trehalose, or the components that are used in embryo or oocyte vitrification. Now there are two methods of vitrification, freezing. One is the slow freezing, the other one is a rapid freezing. In slow freezing, otherwise it is called the equilibration freezing. The equilibrium is the cryoprotectant. We have a programmable freezer to lower the temperature very gradually at the rate of 0.3 degree per centigrade, per minute. And then when it goes down all this happens in a programmable instrument, where there is an instrument which will, it is programmed to take the embryos or the tissues that you keep at that rate, that is 0.3 degree per minute. When it reaches like -6 or -7 degrees centigrade, to induce ice crystal formation uniformly, we go ahead and seed the column of media there. Lowering the temperature gradually permits a very slow growth of water crystals in the extracellular space. The growth of ice crystal induces cell dehydration and increases the intracellular concentration of the cryoprotectants. After the slow cooling steps of about -50 degrees, the intracellular concentration of the cryoprotectants reaches the threshold, allowing intracellular vitrification. The straw containing the embryos is then or the oocytes is then plunged into liquid nitrogen. When warming the embryos or the oocytes which were frozen through slow freezing, the straw in which we are frozen is warmed in a water bath at room temperature until disappearance of the last ice crystal, which takes about 10 to 15 seconds. And then the embryos are washed immediately into the thawing solution, which is mostly consisting of only sugar. So that is one pictorial representation of how we used to do slow freezing. We have this machine into which we will keep the straw, and then this machine goes at a rate of 0.3, reducing the temperature at the rate of 0.3 centigrade per minute until it takes to about -6 to -7, when we have to seed the media manually like this. There will be the straws like this, and then you will have the media, and we will be manually seeding the media at this point at the junction, which will cause the ice crystal formation in the extracellular space. After this, they go straight into the liquid nitrogen. What are the advantages and disadvantage? The advantage was that you can freeze a lot of embryos at the same time. The disadvantage were quite many. One, it caused a lot of intracellular ice crystal formation, which in turn damaged the cell wall and structure, in turn giving us very poor survival of the embryos. And the other disadvantage was the heavy investment in the infrastructure. As against this, from 1985, we have known the existence of another process of cryopreservation, which is the vitrification, which is the ultra fast freezing method of cryopreservation. It induces solidification of the cells and the surrounding solution into a glass-like or vitreous solution without formation of an ice crystal, which is the major advantage. But how do we attain this thing? This is obtained by increasing the concentration of the cryoprotectant to the view of at least 6 to 7 molars, whereas in a slow freezing, the cryoprotectant concentration is maximum 1 molar. So as the concentration of the cryoprotectant is high, there is increased dehydration of the cells. And this also, rapid freezing means extremely fast freezing rate and extremely fast warming rates. As I told you, the concentration of the cryoprotectant is as high up to 6 to 7 molars. And this is very toxic to the cells. The cryoprotectant only in low concentrations is not toxic, whereas at the concentration of 6 to 7 molars, it's quite toxic, which is why the manipulations in vitrification is done only at low temperatures. And equilibration. The first thing is we cannot expose the embryo straight or the oocyte straight to the tune of 6 molars. First, there will be an equilibration which will happen at the concentration of 1 to 1.5 molar cryoprotectant concentration, and then it is exposed to the vitrification solution. And because of the cryoprotectants is low molecular weight and they have high permeability, it can be less toxic only at lower temperatures. The high I'm sorry, I think there is a power shutdown. I think we're back. Yeah. There is a very high concentration of the non-permeating cryoprotectant as well, up to the tune of 1 molar concentration. This is also added up to the concentration of the cryoprotectant in total. So 6 plus 1, 7 molar concentration is what we are looking at. The larger molecular weight disaccharides such as sucrose or trehalose or the non-permeating cryoprotectants that we use. The end concentration of the non-permeating cryoprotectant is added to the vitrification solution. Here, as opposed to the slow freezing where the temperature was reduced as 0.3 degrees per minute, here from the room temperature, which is at 27 degrees, the solution is directly plunged into liquid nitrogen. The cooling rate is it's approximately about 20,000 degrees centigrade per minute. And because of that, it hugely depends on the device and the volume, which we'll be discussing soon. So this is in slow freezing where you would have dehydration plus a lot of ice crystal formation in the extracellular, whereas in vitrification, it's completely the entire cell and the extracellular media available, or water available is vitrified and there is no ice crystal formation. When warming, again, it has to be extremely quick as well. The vitrified cells must undergo warming as rapidly as the cooling rates were to avoid crystallization. The vitrified material again is immersed directly from the liquid nitrogen into the warming solution, which is the first one is maintained at 37 degrees centigrade. So it goes from minus 196 to 37 degrees within a matter of 1 to 2 seconds. What are the advantages of the vitrification process? A, it is simple and fast. B, it prevents ice crystal formation during the vitrification process, which successfully eliminates the major factor that can cause the cell damage during the slow freezing method. As I had explained the procedure of slow freezing, the vitrification process is what we do is we take the embryos or the oocytes and they are equilibrated in the equilibration solution, which is a solution with about 1.51 molar concentration of the cryoprotectants, and then they are exposed there for about 7 to 9 minutes, and after which the embryos goes into vitrification solution to a maximum of a minute to maximum 2 minutes, after which they are plunged straight into liquid nitrogen. So that is just a picture I just wanted to show you. I wanted to show a video, but unfortunately, since it's not working, I thought we will have at least a picture. So that is the treatment. Those are all the blastocyst or the morula or that is the 8-cell embryo or a zygote before before treatment with the cryoprotectants. Once they go into the cryoprotectant, that is any solution, as you see in the second column, see how they start dehydration. So all the cells undergo dehydration. After that is in the equilibration solution. They first start dehydrating, that is they start losing the water, but as the cryoprotectants replace the water in the cells, it starts to re-expand and they almost come to the size of the pre-treatment size as well. But then in the fourth column, you can see they are put into, this is the column when they start putting it into the vitrification solution. The moment the embryos are put into the vitrification solution, there is absolute extreme brutal dehydration of the cells and they almost becomes translucent under the microscope, which is why we have to be very careful when we are viewing these cells. Look at the dehydration as compared to here as to here. This happens in a matter of few minutes, over a matter of like 3 to 4 minutes or so. This is within the next, this happens in 5 to 10 seconds. See how dehydrated they become. But once during the warming, they do regain all their hydration back when done properly. So the advantage again is that in vitrification, it simply involves moving the cells between two dilutions, loading them into the vitrification device and plunging them into the liquid nitrogen. And the second advantage is that no special equipment or investment is required for the implementation of vitrification. However, the practice is quite a lot as compared to slow freezing. The learning curve is also quite a bit, and the skill that we have to get by practice is quite a bit in terms of vitrification. Comparing slow freezing to vitrification, slow freezing is like slowly going down on the temperature before taking the plunge, whereas in vitrification, the plunge is straight down. There is no slow and steady thing. It's just straight in a plunge. Those are all the various differences that we do have between slow freezing and vitrification. But I would just like to show you a pictorial representation of the differences that we can have. This is an eye that has undergone slow freezing as opposed to one that has undergone vitrification. The same way, this is an ice crystal formation in a DDPS. In slow freezing, this is in vitrification. Again, this is slow freezing and that's vitrification. So that's a difference that I would like to you to have it in your picture in a pictorial frame that is the difference that we do see between slow freezing and vitrification. Just imagine if this amount of intracellular ice crystal formation happens in a cell, how much it can survive when we warm the embryos or the oocytes. And that is the component of the slow freezing and the vitrification solution. As you can see, this is the freezing and the thawing kit. This is the component of the slow vitrification. This is the equilibration solution, which is like 7.5 to 7.5. Whereas in the vitrification solution, you see that 15% of DMSO plus 15% of ethylene glycol and 0.5 molar of sucrose is also added. Whereas, as I told you, the thawing solution is nothing but sugar solutions. Like it is first goes to 1 molar sucrose, then to 0.5 molar sucrose, and then the washing solution. That is again a pictorial representation of what happens in during vitrification and the slow freezing. In any oocyte or an embryo, as water goes out, the cryoprotectant replaces the water. In slow freezing, you have ice crystal formation, especially in the extracellular space, whereas in vitrification, both the extracellular and intracellular, they are vitrified, that is, there is no ice crystal formation. So now, how did we start having better results with cryopreservation? So as you can see, from 2007 onwards, the exponential increase in the freezing programs of all the embryos and eggs in USA. This has been primarily attributed to the improved success rates we have with cryopreservation. The results in a success, it means survival, pregnancy rate, and live birth rate. So all this put together, we've had very good survival. That is because we shifted from slow freezing to vitrification in toto. This, I'm just going to only show very few but very optimal and the most important milestone publications that came out comparing slow freezing and vitrification results in both the in oocytes, embryos, cleavage stage embryos, blastocyst, and in all these three. So this is a meta-analysis by Laura Rinzi and her team, where they did publish. They did a meta-analysis of all the publications that has come in this aspect, and this is the meta-analysis of the publications in comparison of slow freezing to vitrification in terms of oocyte. As you can see, all the papers do support have or favoring only vitrification for oocytes. Primarily, why is vitrification better for oocytes? What we have to understand is physics come into play a lot more than we can imagine when cryopreservation is being done. The volume of the oocyte is huge. The volume to surface area, the ratio is quite less, which means for that amount of volume, the surface area that we have for that for in the oocyte is quite less, which means the amount of surface area there is for the cryoprotect to seep into the cell is quite less. And that is why the slow freezing was not a great phenomenon to use in terms of oocyte. Whereas in vitrification, because of the changes made in the vitrifying media and B, basically of the technique, we've been having a better outcomes in A, survival rate, B, the fertilization rate, C, and the pregnancy rate with the vitrification in oocytes. That is another very important publication which came out as well. They had one of the earlier 192 oocytes that underwent slow freezing as compared to 262 vitrified. As we can see, the survival was 62%. Here it is 82%, and the MI survival everywhere we see that the survival rate of the oocytes following vitrification was significantly higher than the survival of the oocytes in using slow freezing. And that is the results or the meta-analysis finding following the comparison of slow or vitrification for cleavage stage embryos. Again, we can see that it is favoring vitrification again. So again, this analysis, this meta-analysis again said that the vitrification is better for even cleavage stage embryos because the survival rate of the cleavage stage embryos was significantly higher in vitrification than in slow freezing. That's another one. A comparison of slow freezing to vitrification in cleavage stage embryos and blastocysts again. Both, this was a publication that came out first in 2008, but then after that we had Laura Rincey's, in between we had Cochrane, so many publications, but this was one of the first meta-analysis that came out in 2008, which still favored vitrification. The Cochrane in 2014, it came out with a review in regard to oocyte survival, comparing slow freezing and vitrification, and which also showed a higher survival rate, oocyte survival and fertilization, and embryo quality were higher using vitrification than in slow freezing. However, at that point of time, there was not much of live birth rate, but right now we do have much more live birth rate in oocyte freezing. It is vitrification that has changed the way ART is practiced as of now, which has helped us in establishing OHSS free clinics as of now. So, how the first step that how we improved cryopreservation rates was from shifting from slow freezing to vitrification in toto. So, there is vitrification of oocytes, vitrification of cleavage stage embryos, and vitrification of blastocysts right now. In these, we don't. The only place there is a contention is when we are using it for ovarian cryotissue, ovarian cortex vitrification. Because of the thickness of the tissue, the only babies that are being born using ovarian cortex freezing is through slow freezing, but there are a lot of centers which are using vitrification right now for ovarian cortex as well, but yet it is still experimental. In the experimental, we are yet to decide whether slow freezing or vitrification is the way to go in ovarian cortex. But however, in all other specimens such as the oocyte, cleavage stage embryos, and the blastocysts, vitrification has definitely shown to have better survival rate and give us better, more number of embryos, better embryo quality. All this has translated definitely into increasing the live birth rate. Now, so we have established that vitrification is the way to improve cryosurvival rate. Then how do we improve our technique in vitrification? What are the tips and tricks to improve the survival rate even in vitrification? In vitrification has got a, as I told you, remember, it has got a long learning curve. So how do we improve our success using vitrification? Let us understand one thing, that vitrification is a beautiful and elegant play between the cryoprotectant concentration, the media volume, the cooling and the warming rates, and the device that we are using. It is a beautiful power play between all this stuff. And what are all the variables? The type of cryoprotectant, the concentration of cryoprotectant, the type of the storage device, the type of storage, the cooling rates, warming rates, timing, and the temperature of the working surface, the stage of the oocytes and the embryos that we are freezing, the basal media and the buffer concentration, the exchange protocols, and the device that we are loading them into. There are so many variables that we have, but something that has been constant. Like for example, when we started doing vitrification around 2006-7, we had to prepare our own vitrification media and the warming media, which there was a variation between batch to batch. But right now we do have commercially available vitrification and warming kits, which are produced and they are tested, they are embryo tested. They do come with a certificate, and their batch to batch consistency is very good, and hence the cryoprotectant constant, what now we are constant is the concentration and the type of cryoprotectant, the basal media buffer concentration. All these are constant right now, which makes our life much easier. So what is the first step to making a good vitrification program? A, choosing our embryos and choosing our oocytes. What we have to understand is vitrification will not improve the quality of the embryo that we are putting it in. It only has got the capability to make the embryo have suspended animation, which means if we do the technique properly, we have extremely less probability of damaging the embryos. However, we have no way of improving the quality of the embryos just because by the process of vitrification. So what you put in is what you get out. If we freeze poor quality embryos, we take back poor quality embryos. We freeze very good embryos, we take back poor, very good embryos. In regard to oocytes, the current gold standard is to freeze meiosis 2, metaphase 2 oocytes. So that is the gold standard to freeze right now. However, we can freeze germinal vesicle to any of that, but then the gold standard now is to freeze M2 oocytes. And there is a protocol on how to do it. In oocyte freezing, it is better that we have decided that if we are going for oocyte freezing, which means once the oocytes are retrieved and then we denude the oocytes 2 hours after the pickup, and then immediately after denudation we go ahead and freeze the oocytes. When we are thawing them, we thaw the oocytes and then culture the oocytes for another 2 hours before we do ICSI on them. This timing interval is very important for the recuperation of the oocytes pre and post freezing. The next step is to keep appropriate temperature of the working surface. We know that for vitrification, there are two temperatures that are involved in. One is the temperature of the solutions that we are using, and two is the temperature of the working surface. We have to understand a basic principle here. The temperature of the working solution and the temperature is because to regulate the movement of the cryoprotectants through the cell membrane. As we all know, cell membrane is most permeable at 37 degrees, and beyond that, yes, it undergoes a damage, and then hence it is like as it undergoes damage, there is no mechanism, there is no proper mechanism to check what goes in and comes out. But then at lesser temperature, 37 degrees is the optimal, but then at the lesser temperatures, the movement of the through the cell membrane is lesser at lesser temperatures, and it's optimal at 37 degrees. So at 37 degrees, when you are performing these procedures in cryoprotectants, which is a toxic material, there will be a sudden influx of the cryoprotectant into the cell, which means we are accumulating a lot of toxic materials into the cell. And that is why when we are performing the vitrification at 37 degrees, the timing of the exposure of the cells to the solutions is minimized. Such as if we are keeping the solutions at room temperature, which is between 24 and 27 degrees, the exposure of the embryos, for example, the cleavage stage embryos in equilibration solution is anywhere between 7 and 9 minutes. As opposed, if we are performing the same at 37 degrees, the exposure time is reduced to 2 minutes. While performing the vitrification at room temperature, the exposure of the cleavage stage embryos to vitrification solution is 1 minute, that is 60 seconds, to a maximum of 120 seconds. While if we are doing it at 37 degrees, the exposure time must be limited to only a maximum of 30 seconds. This is the difference that we always have to have in mind while performing vitrification. Why this is important? Because the cryoprotectants are toxic, and if you are exposing at 37 degrees for 10 minutes, as like how we do in room temperature, we are definitely the sure shot mechanism to kill the embryos. The timing is extremely important. As I showed you how the vitrification solution dehydrates the cells, the exposure of the oocytes or the embryos to the vitrification solution must be timed to a maximum of 30 seconds at 37 degrees, or to maximum of 120 seconds to at room temperature. And that is very important, because Vitrification solution is a very highly concentration of cryoprotectants to the tune of 6 to 7 molars and hence is very toxic to the embryos. And the cooling rates. So now something that we have to understand, if you see here, what is the cooling rate if you are using 0.25 ml straws like how we used to do in slow freezing? It is minus 2500 degrees per minute. While if you are using it much smaller volumes like the cryo loop or the cryo top or the cryo whichever other method that you're cryo straw, the cooling rate can be as high as minus 25,000 degrees centigrade per minute. When we plunge it straight into the liquid nitrogen, we want extremely cooling rates for optimal vitrification. At minus 2500 degrees centigrade per minute, which is in large volumes, the vitrification is going to be improper, which means there will be a lot of external ice crystal formation in the extracellular space, causing damage to the embryos when we are warming them. And that is how we minimize the volume of the vitrification solution surrounding the cells at the vitrification step. For example, when we are starting, we would have so much amount of vitrification solution, but then we aspirate them back and we would leave only one layer of vitrification solution surrounding either the egg or the sperm. But be very careful that we must not aspirate every bit of the vitrification solution. There must be one layer of the vitrification solution surrounding the oocyte or the embryo. So that is the next trick. The volume, the first thing is to have the temperature, maintain the rates of the temperature in cooling and warming rates, and then to have the timing is very important. Another trick is, for example, as I told you, vitrification in practice is moving the embryos or the oocytes from one solution to another, which has got extremely different concentrations. The equilibration solution is 1 to 1.5 molar. Vitrification solution is 6 to 7 molar. So how do we reduce the osmotic shock to the oocytes or the embryos when moving from one solution to other? The trick here or the key here is we load the pipette with the solution which is of the next concentration, of the higher concentration, and then pour that solution surrounding the oocyte or the embryos in the lower concentration solution, and then pick up the embryos or the oocyte. That way the osmotic shock that the embryos or the oocytes will be much lesser. And keep the liquid nitrogen container right next to us. The embryos or the oocytes, after they are in the liquid vitrification solution, must be in the air while going to the liquid nitrogen container to a maximum of 1 or maximum 2 minutes, 2 seconds, and that's the timing allowed. And the same goes for warming as well. So the swiftness in which we put the gametes or the embryos into the liquid nitrogen is very important. It cannot be in the air for 5 or 10 seconds. And please always check the expiry dates of the solution that you are using, because these are very, very sensitive solutions to the embryos and the oocytes. Please check them because it has got sucrose and they do have an expiry date. And always, and another thing that I would like to mention here is before shifting the oocytes or the embryos from the equilibration solution into the vitrification solution, keep them under the microscope and check once if they have regain their volume. As I showed you in that picture, after the equilibration solution, the embryos or the oocytes do regain their volume. They do usually come up to their pre-equilibration solution volume. So it is imperative that we check once. If they have not regained their volume, leave them in the equilibration solution for 1 minute more, and that will definitely help us in improving the success or the survival rates in vitrification. As much as we talk about the cooling, I think the more crucial step is warming. The warming is equally important, or rather, let me say, more important for the success or the survival of the gamete and the embryo in the process of vitrification. As I told you, from the liquid nitrogen container, when we put it, we have to plunge a gamete or the oocyte or the embryo straight into the warming solution, which is maintained at 37 degrees. The time that it travels in the air is maximum 1 or 2 seconds and not more than that. So it has to be rapid, quick. For that to happen, we have to have the readiness, which means the dish and the pipette, everything, and the liquid nitrogen container should be very close to us. The dish with the 37 degrees and the pipette must be close to us. We cannot be doing anything when after it has gone on the air. And please choose your vitrification solution and device that you are happy with. All the vitrification solutions and device are very good. You just have to make sure that what is you are happy with, meaning which gives you the best results. Please, you can try a few and then you can select the one that is more adaptable to you. But please, prior to using them on a patient, on a clinical patient for themselves, please practice on discarded embryos or discarded oocytes or something on that thing. And practice is the most important thing to be done before you actually work on a patient's gamete or an embryo. And another important point is whenever you have a vitrification kit or a warming kit, the manufacturer would have given you a protocol. Please go through the protocol umpteen number of times and follow the protocol to the T. That is because they would have conducted the experiment more like 1,000 times before they would have given you an optimal protocol to use using that particular solution. Hence, please use the protocol to the T. But after you gain confidence, after you have as much experience as a lot of experience, you can start changing the protocol to get better results. But until then, please follow the protocol suggested by the manufacturer. As I said, the manufacturer looks through so many aspects before giving us a vitrification or a warming solution. They have to have a buffer solution which should be sensitive. This I've taken in terms of oocyte because oocyte is a very tricky specimen to vitrify. They have to look at the buffer solution, the cryoprotectant, the macromolecules, the salt composition, and the substrate. All of this has to go with in terms of what is optimal to the oocyte and the embryos. They have done a million experiments before they give us that particular media and the protocol. So the successful vitrification requires minimum volume of the holding media, which should be about 1 microliter surrounding the oocyte or the embryos. It has got increased viscosity because of the high concentration, which we don't have to worry anything about if we get it in the commercial media. We have to maintain high cooling and extremely high warming rate. We have to use the device and we have to practice on the device before we use it clinically. Direct plunging into liquid nitrogen and the time the gametes or in the air must not be more than 2 seconds, 1 if not 2 seconds. The next question that always comes to our mind or that always we have a doubt is whether to use open or closed device. So what we have to understand is that the post-thaw survival is quite high using an open system as compared to the closed system. Why do we want a closed system? Why are we bothered? We are worried of the chemical and microbiological contaminations that can happen if we don't use a closed device. But however, since the cryo survival rate is very high, most of the centers do use open system, especially for oocytes, and closed system can be used in terms of embryos. Whereas and another important point is the survival rate, the meiotic resumption rate, and the maturation rate of the oocytes was not significantly different when vitrified oocytes were stored in either vapor phase or the liquid nitrogen phase. So both are fine, but in oocytes, open is better, but then for embryos, closed is also is good. The next question that we have when it comes to blastocyst is, should we collapse or not to collapse? However, right now, the publications have said that collapsing the blastocyst prior to vitrification has got a higher survival rate. But however, the implantation rate or the pregnancy rate was not different between the collapsed or the non-collapsing group. And hence, right now, the dictum is to have not, we don't usually collapse prior to vitrification because we don't have much difference in the implantation rates. In terms of contamination, which we are always worried about, it has been demonstrated that cross-contamination can occur in liquid nitrogen. But however, there has been no incidence um, of any case where we've had cross-contamination because of liquid nitrogen. But however, the liquid nitrogen that we use in the open system, we throw them away. We don't use them for on another set of embryos or oocytes. That's the that is the precaution that we need to take in the when we are using the open system. Gabor Baita is a big proponent of the open device, and he has come around and stated way back in 2009 and after that as well. He's also a pioneer in terms of cryopreservation. He stated that none of the reported infections after insemination of embryo in humans or domestic animals can clearly be attributed to the application of the cryopreservation and storage, and to ensure rapid cooling in some vitrification devices requiring direct contact, sterile liquid nitrogen can be used. And as well, he also has gone ahead and said that they have failed to demonstrate the same efficiency in the closed devices as compared to the open devices. Hence, open system is the norm for oocytes. Closed systems can be used for embryos. However, when we are using the open system in embryos or in the oocyte, that particular liquid nitrogen that is used should not be reused. However, I'm not sure if you all have heard, we just had a recent, in 2 days ago, we had a baby. The couple's baby was frozen 27 years ago. And it was transferred into a woman who was 20, some 30 years or something like that. And she gave birth 2 days ago. And apparently the embryo is only 2 years younger to the mother. So that is what we have achieved using liquid cryopreservation. The earlier record was a 24-year frozen embryo. As per my personal record, I would say a 10-year frozen, 11 years is what the maximum number of embryos frozen that I have transferred and had a live birth with. Is that all? Is that all? Are we satisfied? No, we are never satisfied in terms of achieving success or survival. We wish to have further course of research into examination in regard to the manipulation of the oocyte cellular composition to improve the cryotolerance. Also, more elucidating is the more accurate or the insightful indicators of success, which is crucial for the continued improvement of oocyte cryopreservation and embryo cryopreservation. Thank you very much, and I'd be very happy to take any questions.
Thank you so much, ma'am, for that enlightening and elaborate session. We can go ahead with the questions with your permission.
Yes, please.
Yeah. So, Madam Dr. Nair is asking, how can we improve quality of oocytes? Is it genetically related? And if oocyte quality is not good, can we improve it in next cycle?
Oocyte quality is it's an enigma. It's something that I wish I knew how to improve oocyte quality. Unfortunately, but there are various factors that we can look into. The oocyte quality depends on the yes, as you rightly said, the genetic material of the mother, which we can't do anything about. But the variables that we can do something about are and another thing that is very important factor for the oocyte quality is the maternal age. So, which also we can't do anything about. But something we can do about is the stimulation. The controlled ovarian stimulation plays a very major part in terms of giving us good quality oocytes. So, a strict, good ovarian hyperstimulation does give us better oocytes. Apart from that, whenever we do a fertility, it is good to give the patient the reproductive vitamins so that it can improve the quality of the oocytes, that maximally increase the quality of oocytes that we can have.
Sure. Thank you, ma'am. The next question is, what are the advantages of blastocele reduction, and what is the best technique for blastocele reduction?
You mean collapsing?
Blastocele reduction.
Oh yeah, blastocele reduction.
Yeah.
Blastocele reduction is very simple. We can just, you can either keep pipetting it out through the pipette and then reduce it. That is the most non-invasive way of doing it. And that is usually practiced. You can go ahead and do a micro manipulation as well. But however, the most common thing is to pipette it out so that we can reduce. However, we don't, generally we don't reduce the blastocele because we are able to have good survival of the blastocysts without reduction of the blastocysts as well.
We'll take the last question, ma'am. Which method, slow freezing or vitrification, is best for sperm freezing?
That's a very good question. Slow freezing or vitrification both are unfortunately or fortunately given us the same results in terms of sperm freezing, but because of the cytoplasm is so less there that it doesn't actually matter. But we could have better results in vitrification when there are extremely few number of sperms there. You can freeze them in droplets and so that you can find them. However, because the numbers of the sperms are so high, whether it's slow or vitri doesn't seem to have a major effect. But however, if you have extremely like 10-15 sperms in the whole sample, you can go ahead and do a vitrification.
I think one last question has just popped in. I will just ask it. What is the current consensus for fresh versus frozen transfers? I mean, it's been a debate for a while now. Freeze all or fresh transfers. I mean, what is the consensus right now?
See, the consensus is this: the scientific publications have shown this. We all know that there is a lag in the endometrium post any COH. But however, there was a trend which said that do freeze all for everyone, and it is beneficial. But now we have been questioning that presently, and there has been publications which have said that freeze all is beneficial only when you have a hyper responder. In
Right.
normal or a poor responder, you can go ahead and have a fresh ET. If your endometrium is fine, please go ahead and have a fresh ET, and it gives the same implantation and the pregnancy rates as that of a frozen embryo transfer. However, in hyper responders, because we want to avoid OHSS and the supernumerary eggs and the high levels of estrogen around, the endometrium is lag is so much that we don't wish to go ahead for the fresh embryo transfer. They are the people who must have all frozen freeze all cycle.
Thank you so much, ma'am, for answering those questions. We would now like to request you to sum up your session today with some key takeaways for the benefit of our audience.
Okay. So in terms of cryopreservation, how to improve our success with cryopreservation? One, we have shifted to using only vitrification. In two, we have to perfect the method of vitrification, which needs a lot of practice. Practice makes us perfect in it. And when we are using oocytes, we definitely like to use open device as against to embryos where you can choose either to use open or a closed device. But another three is when you're using an open device, a liquid nitrogen that you've used, please don't discard it or don't use it for on another patient. And all the tips that I've given you to improve the success or the cryosurvival in vitrification are very, very important, and keep them in mind every time we do a vitrification. And every vitrification is, we must approach it as our first vitrification with that amount of caution, because um, as people who have done a lot of vitrification would have observed and know that the moment you put the embryos or the oocytes in vitrification solution, it becomes translucent, and that's the best way of losing embryos or gametes. So every vitrification that we do, we must approach it with the caution as if it is our first vitrification, and that way we will not lose the embryos or damage the embryos.
Thank you so much, ma'am, for summing it up for us. On behalf of Bharat Serums and Vaccines senior leadership team, I would like to thank you for taking out time and doing this session for us. It was a really excellent session, and I hope our audience enjoys it. At the same time, I would thank the audience for their patient listening. Thank you so much, ma'am.
Thank you.